Okay, so we're going to be discussing a topic called improper integrals, and you might be wondering, well, what the heck is that? Well, when you think about an integral, suppose it's from some bound a to b of some function f of x dx, okay? Let's say that this right here represents f of x, this blue function graphed here. Well, we were concerned with finding before the area from one point to another. Suppose a to b was this region that I'm shading here in yellow. Okay, well, what happens if instead of, going from A to B, all right, let's say you want to go from some point A, all the way to infinity. Basically, you want to find if that area, adds up to equal anything, all right? So what we do is we have to evaluate this using what we call improper integrals. So the integral then goes something like this, all right? This one in particular would go from, suppose, a to infinity. So what we would need to do is we would need to rethink this in terms of the concept of limit. Okay, that's what makes this improper. So suppose that we say, well, let's just assume n is infinity. So let's say the limit as n goes to infinity of a to the n of f of x dx. Well, then we would just integrate this function the way that we normally know how to do that. Okay, and so if we get a number, if we get a limit that evaluates to some number, we say then that it converges, and we can state what it converges to, what the area would converge to. If we get a limit that does not exist, however, we say that this integral is divergent. It diverges, okay? So what we're going to do is we're going to take a look at some examples of what we call improper integrals. And every integral technique that you've learned up to this point is fair game, okay? They're in integration by substitution, integration by parts, integration by partial fraction decomposition, using integral tables, trigonometric substitution. So all of that is fair game here. Okay, you've learned enough techniques at this point in time that you should be able to address how you would integrate something. So we're going to go ahead and take a look, and we're going to take a look at the very first problem. Let me move this out of the way here. Let's say that we have the integral from, let's say, 6 to infinity. Okay, and it could be any number, but 6 to infinity in this case. And we're going to have dx over x squared minus 25. So the first thing I'm going to do is rewrite this using my limit notation. And I'm going to say, well, this is just the limit as n goes to infinity of 6 to n of dx over x squared minus 25. All right, now I'm looking at this and I'm thinking, okay, was this looks familiar? Was this on an integral table or something like that? But in this case, it's actually not. This one right here, you would actually have to decompose, and you'd have to use, I think the easiest method here would just be to do partial fraction decomposition. So I'm going to make that note here that I'm going to integrate, all right, integrate by partial fraction. All right, partial fraction decomposition. And I think it takes me longer to write that out probably than maybe to actually solve the partial fraction decomposition, because this one's actually not that bad. So what I'm going to do here is I'm going to break this up into its two factors. And I know that this is a difference of two squares. So it's x plus 5 and x minus 5. So let me consider that. And I'm going to do that in a different color so that we know that it's not part of our integration, but it is part of what's leading up to the integral. All right. So let's see here. If we have 1 over x squared minus 25, this is equivalent to a over, suppose, x plus 5 plus b over x minus 5. And what we're going to do here is we are going to multiply straight across by those two factors in the denominator, x plus 5 and x minus 5, to come up with an equation basically that we can utilize to solve for a and b. So when I do this, it's going to clear out the denominator in the first fraction, leaving me with 1 equal to, and in the second case, it's going to cross out this x plus 5. leaving me with an a times x minus 5. Okay, and then in the next case, it's going to be b times, and then the x minus 5s are going to eliminate, and it's going to leave me with b times x plus 5. There you have it. Now what we're going to do is we're going to pick wise choices for x in order to solve for a and b. So the first thing I'm going to say is, okay, well, right here, if x minus 5 equals 0, x equals 5. And here, if x plus 5 equals 0, then x equals negative 5. So those are the numbers I'm actually going to pick. Let's start off with x equals 5. If x equals 5, I have 1 equal to, this eliminates itself, so that's gone. I have b times 5 plus 5. Okay, so what this leads up to is 1 equals 10b. So then I can state here b equals 1/10. All right, now I am going to come back to this original equation, and the next thing I'm going to state is x equals negative 5. So I'm going to say 1 equals, and then a times, and let me take this back a second. So setting x equal to negative 5 will eliminate the b component here. And we're going to say 1 equals a times negative 5 minus 5. So what does this lead to? This says 1 equals negative 10a. And therefore we can say a equals negative 1/10. And now we are ready to do our whole integration, if you will. So let's go ahead and take a look at what that might be. All right. So this, when we come back to what we were talking about, it was the limit as n goes to infinity, and we're going to say the integral from 6 to n of, in this case, a was negative 1, so I'm going to put negative 1 over 10 times, and then it was x plus 5 from back over here, okay, when we broke it up. All right, and then I'm going to say plus 1 over 10 times x minus 5. Again, that's the b component there. And then, of course, we cannot forget dx. So now what I'm going to do here is I'm going to try to simplify this just a little bit. And by doing so, I'm going to factor out the 1/10 from all of this. So again, we still stick with our limit. All right, but I'm going to factor out the 1/10 from the integral. And it's still from 6 to n. Now I'm going to play around with this a little bit in that I'm going to move this around just a bit. I'm going to say 1 over x minus 5 minus 1 over x plus 5. Okay, and that's just to, so that it just looks nicer. I just move this over here and that over there. And that's all that happened there. All right, so nothing really to it. Don't get scared about what happened there. You didn't miss anything. All right, so what we're going to do here is we're going to do some very basic integration, and that is a very minor U substitution. And what we're going to do is we're going to say, okay, well, in both of these are our U's. But if you have the integral, suppose, of 1 over u du, it's just going to be the natural log of u, all right, plus c. Of course, this is a definite integral, so we're not going to write plus c, but I'm just kind of refreshing your memory about that rule there. So this one actually becomes very simple. The limit as n goes to infinity is of 1/10, all right, and it's going to be the natural log. So I'll factor out the 1/10, natural log of x minus 5 minus the natural log of x plus 5. And it looks just like that. And this is going to be evaluated from 6 to n. All right, now I see this right here, and I'm going to apply the laws of logarithms. So I'm going to put laws of logs for short. All right, and so what does that mean for me? Well, that means that I'm going to take the limit as n approaches infinity of 1/10 of, and it's going to be the natural log of x minus 5 over x plus 5. And this right here is what I'm going to evaluate from 6 to n. And so I think now I'm ready to kind of plug in my n and evaluate, push anyways, get closer to evaluating the limit. limit as n goes to infinity then of 1/10. And now let's go ahead and plug in. It's going to be the natural log of n minus 5 over n plus 5. We close that out. All right, minus the natural log of 6 minus 5 over 6 plus 5. All right, and we can continue simplifying here, and this one, you know, just becomes simpler and simpler as we work through it. I think the partial fraction decomposition was probably the hardest part here. So let's go ahead and take a look at the next part. Then we end up with, well, this right here is 1, and this right here is 11, and we're again subtracting. So we're going to have, basically, let me write this out for you, the natural log of 1/11. All right, and again, laws of logarithms apply, so we're going to have to divide, but when we divide by 1/11, it's the same as multiplying. So we're going to have the natural log then of 11 times n minus 5 over n plus 5. Okay, and this is basically what it boils down to. Now we're ready to kind of, and I'll say this very lightly, I'll say let's plug in. Okay, so let me draw my little plug here. We're going to plug in this infinity. What the effect of plugging in infinity, basically you have infinity over infinity, because you're infinity minus 5, infinity plus 5. This has the effect of going to 1. All right, so basically we are left with a very final answer of 1/10 times the natural log of 11. All right, 1/10 times the natural log of 11. So this right here is what the area under the curve would approach if we were to continue to go from 6 to infinity here. But the other statement that we can make about this is that this converges, because you may just be asked, does this converge? Does it diverge? Well, it converges, and this is our proof here. All right, it converges, and there is our proof. So let's go ahead and take a look at a couple more examples, and you might find them a little bit easier because the integration technique is easier. All right, so let's take a look at our very next problem. Here is number 2. On number 2, we are going to go from negative infinity to 0, and we have 1 over x minus 1 quantity squared dx. All right, so we're going to again take the same limit approach, and let me move this up just a bit. We're going to say the limit as n goes to now negative infinity. So this is going to change the bound from the previous problem, but it's not a big deal. We're going to go from n to 0. We have 1 over x minus 1 quantity square, and then of course dx. Now I'm going to make the note here about what we should do. All right, this one is a very basic one. This one we're going to do integrate by, and then you might have guessed it already, U substitution. All right, U sub for short. So I'm going to say, well, U equal x minus 1 du equal 1 dx. We've kind of got all of that already. This right here is U. This right here is du. All right, so we're basically integrating, let's see, let me make that note here. Du over u square, which is u to the minus 2 du, which ends up being what? Okay, u to the minus 1 over negative 1, so we put a negative there, plus c. So we don't need to worry about the plus c here, but it's going to be a negative 1 over x minus 1 plus c. That's what it would boil down to if we were doing an indefinite integral, but this one is definite. So we're going to use that result to now take our definite integral, our improper integral, if you will, and we're going to figure that one out. So we've got negative 1 over x minus 1. All right, that's what we're working with. And we're going to evaluate this from n to 0. All right, n to 0. All right, and we take a look at this, and we're going to see, okay, well, what does this look like? This is negative 1 over n minus 1, okay, minus negative 1 over 0 minus 1. And so remember, we cannot forget the limit, and it looks like I did, but it was for a reason, I think. I'd like to think anyways. All right, so we have this right here. All right, And what do we end up with? We end up with a positive, all right? A positive. And then this right here, when we plug in this infinity, basically, you're going to have, you know, something that looks like, excuse me. Let's see here. Give me 1 second to work this out for you. So we had, I'll take it a step back real quick. We had a -1 that we were subtracting. And so this right here has the effect of what? Okay. Oh, I'm sorry. I completely messed up. So let's take it back just a step. All right. We went the wrong way. We should have said -1 over 0 minus 1. I said this looks fishy. Minus -1 over n minus 1. Here's where we were going with this. So this right here is plus. Okay. This right here becomes a +1. Okay. So we have the limit then as n goes to a -infinity of 1. All right. In this case, 1 plus 1 over n minus 1. All right. Now, basically, you're going to have 1 over infinity minus 1. This is going to go to 0, leaving you with a final answer of 1, which we then can say this limit converges. So the area under this curve right over here would be 1 if you were to go from -infinity all the way to 0. So we then say, of course, that it converges. All right, let's take a look at one last example, and then in the following video, we're going to take a look at what happens when we go to, something that diverges. So the next one will converge, and we'll see what that looks like. Let's take a look. Here is number 3. All right, this one is going to go from -infinity to infinity. All right, 9x over x squared minus 1 quantity square. We can't forget the dx. So what we're going to do here is we're going to break this up into 2 separate integrals. First, we're going to take a look at it from -infinity to 0. All right, and then we're going to take a look at it from 0 to infinity. All right, so we're going to go ahead and take a look at those 2 components. And we cannot forget the square, the fact that it was squared to begin with. All right, now let me scoot this over. All right, and tell you how we're going to integrate this. All right, well, what we did here was we broke it up. So I'm going to write break up. And then we're going to integrate by U substitution. All right, U sub for short. All right, so let's go ahead and take a look at what that might look like. And we're going to say, well, U equal x squared minus 1. So what does du equal? 2x dx. Okay, so we're going to integrate both of these basically the very same way. All right, so let's go ahead and take a look at what that indefinite case might look like. Okay, what the indefinite case might look like. So we're going to say, okay, well, you have 9x over, let's see, x squared minus 1, and then dx. All right, we need to include a 2, so we're going to multiply by 2. That has the effect of multiplying by 1/2 on the outside. And we do our little substitution here. So this right here, 2x is our du, and this right here represents our u. And so we end up with something that looks like this, a 9 over 2 on the outside of the integral of du over, and then it was x squared minus 1 square, so sorry about that part, over u square. Okay, so du over u square, which is 9 over 2 integral of u to the minus 2 du, which is 9 over 2 negative, because it's going to be u to the minus 1 divided by minus 1 plus c. So this is a -9 over 2u plus c, which when we back substitute, we're going to get -9 over 2 times x squared minus 1. All right, plus c. So now that we've done that, okay, we basically have our limits set up. All right, the only thing is that we need to go in and specify the two bounds that we're looking at. So we're going to first take the limit, and we can say the limit as n goes to negative infinity, in this case, of, we can say, well, we've already integrated it, so I'm not going to worry about that. But we're going to say negative 9 over 2 times x squared minus 1, evaluated from, and in this case it's going to be n to 0, plus, okay, now we're going to look at the second integral, which we've already integrated. Now we're going to call this one m. M goes to positive infinity, because we're going to take the same integrand, all right? And what do we get? We're going to evaluate it from 0, in this case, to m. So we've already done the hard part, which was the integration. Now we just look at the limits of this and how that plays out. Okay, so let's go ahead and take a look and see the first limit here. All right, the first limit here is going to be, let's see here, write it out, negative 9 over 2 times, basically 0 squared minus 1 is negative 1. All right, minus, and then it's going to be a negative 9 over 2 times n squared minus 1. Okay, plus, all right, and then we have a limit very, very similar to what we had in the very first. It's just in reverse, I believe. All right, we're going to have a negative 9 over 2 times m squared minus 1, minus a negative 9 over basically a 2 times a negative 1 again. All right, so let's see what this looks like here. All right, this right here gives me, and let me clear that out of the way. This right here gives me limit as n goes to negative infinity. We have a negative 9 over a negative 2. It's a positive 9 over 2. Minus makes for plus. And we're going to have plus 9 over 2 times n squared minus 1. Plus another limit. M goes to infinity. This one is negative 9 over 2 times, again, m squared minus 1. Minus makes for plus, but then the bottom makes it negative, so a minus 9 over 2. So now let's go ahead and take and evaluate the limit. Well, you're going to plug in a negative infinity here squared, so it's going to be infinity. 9 divided by 2 times infinity minus 1. Well, that's just ridiculous. 9 divided by something huge is 0. All right, and the same thing happens with the same logic for this part here. So what you are left with basically is 9 over 2 minus 9 over 2. And what do you get? None other than 0. So this right here, all right, while you may think, well, we did a lot of work for nothing, it's actually something, okay? It is convergent. It does converge, all right? And I bet if you were to look at the graph, you would see that the area probably cancels itself out. Okay, you probably have a negative area from, you know, one interval to the other, and a positive area from one interval to the other, and it's symmetric, and therefore it cancels itself out, and the net area is 0 under the curve from negative infinity to infinity. So again, this one does converge. So again, really nice examples here of improper integrals. So as always, I hope this video was helpful, and remember, like and subscribe.